Just when we thought spring came, right? Winter came back. So today we have a little bit of a optional, so to speak, extra credit lecture. We have to finish up what we started last week, right? And you guys had a lecture with Cheng. I had an appointment that was impossible to move. And Cheng came here, I think, and talked about Giibs sampling. How do you feel about that? Did you feel like, did he do a good job or not? Did we understand Giibs sampling? Yeah. A little bit? You can be honest. Cheng is a very smart guy, smarter than me by far. But he's not used to explain things. So he only goes to conferences and talks to people like him. That's the problem. You can't ask him to explaining is a skill in itself, whether you know something or not. But I think he did explain Giibs sampling, and he should have run an example that I gave him to run a code that was in Python. That was saying how to do Giibs sampling on a very, very simple Gaussian joint distribution. You guys remember that? That's part of your homework. You're going to have to implement that code. The code is just 20 lines of Python code, and it's online, but you can't copy it, okay? You have to write it yourself. So let's talk a little bit about Giibs sampling first. Just not the whole story, just a very quick recap. So we have X, it's a multi-dimensional, say D, random variable. So X is, you can write it as X1, X2, up to XD, something like that. And there's P of X, it's a density function, which is a joint. We say joint because it's a combination of D random variables, some dependence and independence between them. So how do we sample a bunch of these data points? You can think of these as an instantiation of these random variables that satisfies this density function, right? It's sample according to that probability, creates a data point that follows that distribution, right? Meaning if I sample a lot of them, I'll end up with a distribution of patients, if these are patients' features, or emails, and these are emails features according to that P of X density function. So how Giibs sampling is a mechanism to do this if you cannot sample from the joint. So if Giibs cannot sample from joint, but can sample each one of these xk, one of them, this is a component, it's not the whole big X, the vector, it's one of them, from conditional distribution, which would be P of what? Xk given all the other ones, x1, x2, up to xk minus 1, right? Then xk plus 1 up to x. So notice in here, this is the one that's missing. That's the idea. Somehow, I cannot sample from the big joint, but I can control or estimate the conditionals. So I can either model the conditionals. Or maybe if I don't want to model them, I can estimate them. There is some magic that I can do on conditionals that somehow I cannot do over the joint of variables, right? So Gibbs sampling in that case, it's a very simple procedure that says loop, right? So this is a main loop, but then inside 4k equal 1 to d, right? Sample xk from distribution conditional, right? That will be p of xk given what I'm going to write here, it's x minus k. This is a notation used in some statistic books. And what this means every component except, okay, this is a simple notation that says, instead of writing everything, sometimes I write this whole thing as x minus k. That means it's everybody except that one that I'm sampling, that component. Make sense? Okay. So sample these, right? And that's it. At the end, the objects obtained, you can say this is my look for t equal 1 to how many rounds I want. This is my xt. Here I'm getting the whole vector one by one, right? This is the first patient, the second patient, and for each patient I'm getting each feature one by one based on conditional distributions. Right? So the main loop is each data point, which is a vector, right? And then inside the second loop is like each component of the vector. Now, this is going to say xt with t equal 1 to t, this whole collection of things that got sampled, patients, are now distributed according to correct distribution p of x, the joint. That is the Gibbs idea, that if you do this properly, eventually you're going to obtain a sample that's distributed according to the joint that you want. Now, in practice, in here, some of these x components, let's say L, where L is smaller than the current one, are from current xt. In other words, if this k is 3, what's the x1 and x2 that I use? The one that I just sampled for this patient. But for the later ones, assuming I sample in order from k equal 1 to d, what about the other ones, the XLs that have L bigger than k? Where do I get those from? Those are the previous ones that I sampled before, right? From previous. So that's some engineering detail that needs to be done there. So that's what's happening in that sample code that Cheng showed, and we can put that online. That's the I don't want it because that's the code you have to write, right, for this problem. It was oscillating. There's two components. The Gaussian had two components, x and y, called in that code, and was saying sample x given the previous y, sample y given the previous x. In other words, y was sampled given the current x for that sample, but the x was sampled given the previous y, the one for the sample before, right? And was oscillating like that, creating pairs x, y's. In that example, d was 2, right? So I'm creating a bunch of pair x, y's, and I think, did he plot them for you? Did you show a plot? You saw how that if you sample a lot of them, that looks like the joint. If you do a histogram, or if you of course, he knew the joint. You can sample directly from the joint, but as a toyish exercise, he didn't use the joint. But he used the joint to say, okay, at the end, my sample of 3,000 objects, or how many pairs did he sample, are distributed according to the main joint. Okay? this Gibbs sampling is a quite useful technique to do a lot of things probabilistically in machine learning, because in machine learning, there's a lot of reason to control conditional distributions without the ability to control the joint. This is not specific to LDA, this particular idea that the joint is difficult, typically exponential. If I have so many components, D components, and every component has a bunch of possibilities or some PDF distribution, the complexity of the joint is an exponential thing. And in machine learning, D could be quite large, right? It's quite frequent that the number of features is hundreds or thousands of features, even after dimensionality reduction. So a joint taking into account all possibilities of combinations of things, it's quite difficult to work with. Not to mention that even if computationally we have enough power to deal with a joint, we wouldn't have enough data to estimate the joint correctly. But conditional distributions are a lot easier in many practical applications. Why is that? I mean, theoretically, this is still a D-dimensional thing, right? But why is it that in practice this is usually easier? What's happened with the conditional? This is how xk depends on the rest, right? It is true that variables are not independent, because if they'll be independent, this will be just probability of xk, right? But it's also true that one particular variable usually depends only on few of them. If you took a machine learning class, depending who's teaching, it's either the first machine learning class or the second machine learning class. There's something called graphical models, and I think some of you may have seen those. They draw these bubbles, right? Graphical models, and some arrows between them, right? Seen that? And what are the bubbles? The random variables. And what are the arrows?
Dependencies.
Dependency. And you notice in all these graphical models, usually one of these random variables only depends on few others, right? And I think that's true. If you look at the patient, they have a lot of attributes or blood tests and all of that. You could say those are not independent, but the dependency kind of form clicks. Even if I run for a patient, 300 attributes, each one of them it may be depending only on 5 or 6 others. So conditionals are a lot easier to model in a lot of data problems. The opposite of this idea, if you like, in this kind of as a drawing, is the neural network, right? In a neural network, arrows represent contributions, right? And what do we have between two layers of a neural network? If, say, from this layer I get to this layer, how are the arrows looking here?
Fully connected.
Fully connected, right? Usually in a neural network, this guy is to everywhere, this guy is to everywhere, this guy is to everywhere, right? And that kind of operation is done with linear algebra. It has to be simple. The only thing that we can afford there is simple multiplications and additions because it's such a dense layer. In graphical models, those are usually sparse. The network can be big, but not that many arrows probabilities to deal with, which makes the conditional our favorites to work with. Now, this is not enough to do graphical models, what I'm saying today, but if you take a class into graphical models, that's the main difference between a network and.
So we have to so to do Gibbs sampling, we have to come up with this
Conditionals. So you need the conditionals or some estimate or some modeling assumption on them because the sample it's going to come from the conditional distribution. So in the homework, the basic stuff that says implement Gibbs sampling, it tells you first that assuming the joint, which is a Gaussian joint, you have to derive the conditionals. There is a link in that problem to a paper that derives the conditionals for you. They're very simple. If you use D equal to, like Cheng had in the code, the conditional turns out to also be Gaussian distributions. So you need to figure out if I have a joint of some parameters, mu and sigma, what are the conditionals of x given y, y given x. You don't need to look at that whole paper. You only need the formula that says what's the conditional of x given y. That's going to be a Gaussian distribution where you have to update the mu's and sigma.
How is like Gibbs sampling related to this Markov change Monte Carlo methods?
Right, that, I'm going to answer that question, but I won't delve into that, because if I delve into that, I kill the whole term from now to the end of April, okay? So we'll answer that specific question, but not any more than that. Markov chains is an entire thing that you have to take a course into that. If you really want to study Markov process and chains, very useful things, by the way, in a lot of processes, modeling, graphical models and all that. A lot of games, a lot of reinforcement learning, they all use Markov processes as models. It's extremely useful thing to do as a project or as a seminar or even as a course related to graphical models. But we can't expand more than just answering the question. You have a question too?
Yeah. So it's related to this paper that you're talking about. So Chang also mentioned this, that because we have a normal distribution, by taking a conditional distribution over one variable, it essentially boils down that represents another Gaussian distribution, a univariate Gaussian distribution, and that's why it becomes so easy to kind of sample from that. But is that also in general applicable for all distributions, because Gibbs sampling works for all distributions?
Good. I'm just about to go into that part next. All right. So let's answer that one first. How does it relate to Markov chains? Now, I can't teach you guys Markov chains, but assuming we have some sort of idea about them, really quick. There was this undergraduate, like secondary grade or high school, like a story. You know, here's 3 restaurants, right? What was the example? Bertucci. I don't know, 3 pizza places. Bertucci, what's another one? Maybe Uno and Pizza Hut, right? And I'm saying, if you go to one of those, what's the chance of staying in it versus moving to this one next round versus moving here, right? So these 3 probabilities must sum to 1. They call transition probabilities. Once I go to this place, what's the chance of, say, Bertucci is very good, so maybe people might decide to go there the second time they want pizza. This one, Pizza Uno, is okay, 0.2, and this is the difference, 0.05, right? These have to sum to 1. And each one of them has this table of probabilities. So this probabilities define a probability transition matrix. Probability, so BH is the probability of going to B given last pizza in H. So if I ate in H, what's the chance of now, next time going to B, right? What Markov chain says, it's called a memory-less transition process. That memory-less states the following. If I am in state B, I just gone to Bertucci, the only thing I'll remember is that I've been to Bertucci. Everything else in the past is forgotten. So memory-less means it only matters where I'm right now. It doesn't matter how I got here. A lot of games are implemented that way. Now, that's a little bit simplific of game playing computers instead of humans, because humans remember more than just the last state. But when you play chess with the Markov chains, it only evaluates the current board. It doesn't matter how it got here. Okay? There's so many ways to get to that current board, situation on the board, but that's the only thing that indicates what I'm going to try to do next, given the current situation, right? So there are many processes that can be modeled that way, given the current state of things, independent how we got here. Here's what our options are to go there and there and there. Markov chains usually correspond to a random process that says once you start here, somewhere, and you move with those probabilities, right? For everyone, you have a fixed transition matrix. Maybe this is 0.5, 0.2, and 0.3 and so on and so forth. So once these probabilities are known, from this what's the chance to move here and here, you can show that eventually you reach a stationary distribution. That is the probability of visiting each node, such that if you move once, if you do the update, that stationary distribution doesn't change. Or in other words, if you have 1 million people eating pizza, and they are distributed, some people here, some people here, and some people here, if they are according to the stationary distribution distributed, once everybody moves to the next restaurant, given the transition matrix, that fraction of people in Bertucci is the same like before. So a stationary distribution, so there's a transition. This is the distribution I, B, phi, U, I, H. So this is a distribution, how many people at round 0, 1, 2, 3 eat in Bertucci, eat in eat in Pizza Hut, right? And there's a transition that says the next probability distribution, this is a vector. It's the old probability times the transition matrix. And you can show that this converges. There is a stationary distribution. Overall, in general, how many people eat in Bertucci Uno versus Pizza Hut, if this gets to be convergent. And there is a mathematical way based on eigenvectors to compute the stationary distribution. So that's a quick intro into Markov chains. They are more complicated than that, but that's a basic example. So why is this related to Markov chains? If I interpret each one of these things as a state, I'm sampling xk right now. The sampling probability, right, acts a little bit like a Markov chain. So suppose we sample xk. What are we going to do next? Sample xk plus 1, right? It depends on how I got xk, what's going to happen with xk plus 1, and then xk plus 2 and xk plus 3 and so on and so forth. This is typically a control process, right? So what will be my states and what will be my probabilities? It's not exactly a Markov chain, but if we want to follow that analogy.
So the states are all in a variable.
I don't think it works that way. Because if the states are the variables, right, I would have to choose what to sample next. Usually in the Markov chains, I go and say, okay, from here, independent of what I'm getting, I have a fixed probability to transition here and here. If my states are the variables, right? Once I sample xk, I'll have 100% probability to move to xk plus 1. It doesn't fit a Markov chain.
Samples?
Who should be one of these states?
The samples that you're actually picking up?
The whole, by patient. That's how I think we have to think about it. One of these states is I sample the following patient, the following blood pressure, temperature, That's my patient. That's what I sample now. Given what I sample, I could sample now that patient or that patient or that patient. Now, this is not, I'm not trying to formalize this mathematically. I'm saying I think that's the analogy that's saying, given the last patient you sampled, move to the next one. And the reason they make the analogy with Markov chains is that because when I'm sampling the next variable, I'm only looking at the last sample variables, not at the whole history. I'm only depending on the last samples that I've done. So each one of these probabilities, it's modeled by the last values I've got, which the first k minus 1 are for the same patient. The last d minus k are from the previous patient. And there's a bunch of parameters that says these are multinomial Gaussian variables or something, right? So each one of those, it's a function of x1. I'm going to write generically x minus k, all the variables except k. and some parameters. In Cheng's code, this was the last variable. If you sample for y, that was x. If you sample for x, this was the last y value, not the whole history, just the last one. And the mu and sigma that he computed for the conditional, right? Because he said the univariate conditional is that. I'm computing in advance the mu and sigma. And now I look at the last value sampled and the parameters, and I'm sampling from that distribution my next variable. So the analogy with Markov chain is done because I only depend on the last variables that I've got, not on the whole history. At least that's my understanding of it. Now, okay, that's the most I can say about Markov chains without delving massively into the subject. The other thing is, okay, so there's an important observation here, which he asked. Okay, so if I know somehow the joint is Gaussian, but for some reason I can't use it, nice, the conditional distribution is going to be a Gaussian, so I could model it or work with the Gaussian distribution. That's because the joint was Gaussian, right? What happens in general, right? What if in LDA, for example, LDA, the joint is not a Gaussian distribution? How do I work with conditional distributions, right? So there is an implicit requirement here that the conditional should be a lot more usable, maneuverable, right, than the joint. If that's not true, then I can't really, the whole principle, which is proven mathematically, relies on this notion that I could somehow get the joint, get the conditional. Now this is, fortunately for us, this doesn't have to be very strict. Sometimes we just make an assumption about the conditional to make it easy to work with. And we think, okay, given this assumption, joint might be that way. And if that's approximate, that's fine. Because we always going to approximate things. Nothing is Gaussian or Poisson or Dirichlet or beta exact. We just make an approximation that makes the math looks nice. But there is a principle of how to do this, right? So that's what I want to talk about next. So to facilitate this relationship between joint and conditionals, let's say I have some parameter. I'm going to call it delta because the typical, I have a later thing. Typically it's called theta, but later on I'm going to need theta for something else. I don't want to cause confusion. You know the base formula, right? Let's just say x, big X here. P of x given delta. So x is the random variable. Times P of delta given P of x, right? Base formula. You guys are very quiet today. Why is that? Something going on? Why are we so quiet? Usually I can't get people to pay enough attention to me, and now everybody's so into this. Are we particularly excited about Gibbs sampling and LDA? I mean, that's good. I really mean it. Very good. But I'm surprised there's so much interest into this topic, and the other ones, which seems far more down to earth, they were not so interesting. Just kidding. So who's P of x in general? This is either a summation. I'm going to write it here as an integral, but you can think of it as a sum. Integral of P of x given delta times P of, this is overall delta, so let's call it delta prime. know what this is. This is saying take off all possible of values of the parameters delta prime. This is a particular delta. This is all possible values delta prime. And then for each one of them, you get the x corresponding to that delta prime, and then you can integrate over that if it's a continuous distribution, or if this is a discrete distribution, if delta prime, it's only 3 possible parameters. Well, how do I do that? This will be the sum of given delta prime times delta prime over all delta prime possible values. Right? If delta prime would be discrete instead of continuous, would be a sum of the numerator options, all of them. This is just normalization. It's saying if this is the joint delta, this is P of X and delta, right? So I take all the possible values and I sum them up to get the normalization, right? Because otherwise this wouldn't be a probability function. Okay, so by the way, I'm pretty bad with integrals myself. I don't know, I got educated in the discrete mathematics, so I don't handle integrals very well. Every time I see an integral in a probability paper, I immediately in my head convert it to a sum. Sounds so much easier to do a sum, because all these equations work that way. I'm not saying you should do that. If you're comfortable with integrals, keep them as integrals, but in general, I think you can think of them as sum in a continuous space. Okay, so now, what's going on here? This is the posterior, right? And this is the prior. So this is true for all models, right? This Bayes theorem holds all the time. What we want the posterior form or model to be the same as the prior form or model. So that's not part of Bayes theorem. This is what we want. I'm going to give you an example in a second of why that is. So this, if we achieve this relationship, that has a name, it's called conjugate prior. If we have this particular property, this again, this is general, this happens all the time. This does not happen all the time. We have to choose those probabilities or the models we work with to achieve this relation. Right? Let me give you an example. Here is the I think binomial distribution. Probability, but binomial distribution has to do with flipping a coin a bunch of times, right? And there's a probability of head or success, right? So let's say probability of head or success is Q, right? So then probability of failure or tail is 1 minus Q, right? So now I throw to get the binomial distribution, I throw the probability of obtaining S heads or successes out of N flips. That's the binomial distribution. What's the chance if if I flip this coin 100 times to get so many heads. So I think we know the formula, right? N choose S, Q at S, 1 minus Q at N minus S. So this is the possibilities, how many ways to choose S out of N, probability of getting a head at power, how many heads I got, right? That's the binomial distribution, right? If this is the distribution I have, then the conjugate prior is, the conjugate prior has to do with the probability over the parameter of that distribution, right? So this is, what's a prior? The prior has to do with the probability of the parameters. But what's the parameter in here? The parameter for this distribution. S is the argument, right? There's a parameter that's fixed in this distribution. Q is the probability of a success, right? That has to do with the coin you have. If you have a different coin, you might have a different Q, right? So in here, that's the probability of Q is, this also has some parameters. So this is called a beta distribution. In parameters alpha and beta. Beta distribution has two parameters. Now the beta function I think it's alpha factorial, beta factorial. Is that right? I forgot. Yeah. So you guys remember this kind of thing? Where this shows up? Is it 1 over this, or I think it's this, right? So 1 over this is what? Is the binomial coefficient, right? You remember in the binomial expansion, what is n choose k? How much is n choose k? N factorial, k factorial, n minus k factorial. Isn't that very related to this thing here? This is effectively 1 over this is like alpha plus beta, choose alpha. Right? Or choose beta, because it's the same thing. Yeah, trouble is this is not mathematical. Now I wish to turn off the camera. This is not mathematical because alpha and betas are real numbers. You can't do this with real numbers. Right? So it's not correct. That's what we want. The factorial is like alpha plus beta, choose alpha. But we can't do it with real numbers. This only works if alpha and beta are integers, positive. So there's a generalization that says, okay, instead of factorial, there is a function that generalizes factorial. So generalize factorial. So instead of alpha factorial, we're going to write a function, it's called gamma. So we're not going to write it with factorials. We're going to write it with this gamma function. We're going to say that is gamma of alpha times gamma of beta, gamma of alpha plus beta. That is for 2. So in a binomial, I have 2 things, right? Like n choose k. But in a this is binomial. But in a multinomial, I have not just k, I have n choose k1, k2, up to kt, with the condition that sum of ki has to sum to n, right? Because in a binomial, I only have k and n minus k. They have to sum to n. In a multinomial, I have splitting n, 20, into a bunch of things that counts that sum to 20, right? So that is the formula for that. The coefficient is still n factorial divided by k1 factorial, k2 factorial, kt factorial, right? The multinomial coefficient. Same thing can happen here. If I want to have a multinomial beta, I have beta of some alpha vector, which is alpha 1, alpha 2, up to alpha t, right? It's a vector. So that function is going to be the product of gamma of alpha I divided by gamma of the sum alpha. Same exact formula, but now with 2 with t things in it. Anyway, in the interest of time, there is a derivation that shows why this, of course, is the conjugate prior of that. We can try to do that, see how far we get. So, following our notion here, that's my distribution, that's my conjugate prior. What I want to show that if I make the product, I'm getting kind of the same thing as the conjugate prior here. Why is that is useful for modeling data? Think about it this way. If I do multiple stage sampling, I start with the prior, right, over my parameters. I sample a bunch of patients. I get the posterior, which says, now what is the probability over my parameters now? After I sample those patients, how do I think of my parameters? Now, if this has the same form as my initial distribution prior, I could use now this as a prior, right, without changing my algorithm at all. I'm saying the next sampling of patients will use this as a prior because it's a different prior but has the same form. If this was a beta distribution, this is also a beta distribution, so I can just keep running my algorithm. And once I get more samples, these times my prior will give me another different beta distribution. That's my new prior. So I can keep going like that, which facilitates a lot of data processes. So let's see how this goes here. Probability of success, failure, given Q is X. This is S plus F, choose S, X at S, 1 minus X at F, right? And the P of X, it's alpha minus X round X. So now that this is my prior, this is my conditional, I'm gonna say probability of Q equal X given success and failures. So this is, X is what's my parameter value, Q is my parameter, right? So this is the density function I'm using as a prior over my parameters. This is prior over parameter. And this is my observations, right? How many success and failures I observed if this is my parameter, my coin bias. How many people with me? Hands up so I can see them. Okay? Should we take it slower? What I've had here, I say this is the coin flipping distribution, right? That's pretty much controlled by my intuition of the process. I think this comes naturally from saying if you flip a coin so many times, if you start counting how many heads would you observe, you're going to notice that that's your distribution if the tosses are independent. We've seen this before, right? If we assume the tosses are independent, every toss has the chance of producing probability Q a head, then the number of heads, the probability that a heads is S will be, that's the chance of getting S heads in a particular order, but then we have to sum it up over all possible orders that have exactly S heads, and there's n choose S ways to get S heads in a sequence of n. Remember high school, right? Counting, right? This is saying what's the exact probability to get a sequence with S heads in it in a certain order, but then summing over all orders that have S heads in them, I get this coefficient. So this corresponds to my understanding of how the coin works, right? This, I came up with it, right? This is saying, I'm not sure what the bias of the coin is, Q. If I know for sure it's 50-50, I wouldn't need a probability. I would say the Q is 50%, and that's 100% chance to be that and nothing else. But in reality, I'm like, okay, I'm not sure what here's the 50% Q, and it might be there. Most coins have that bias, right? But not every single coin has exactly 50%. So maybe some coins have a lower bias. Maybe the matrix that makes the coins is more likely to get a little bit lower than 50, more into the tail section and less into that section. I don't know, right? Depending on how manufactured the coins, not all coins will have exactly 50-50 chance. So then this is a distribution over the biases of the coin. That's what I'm trying to model here, the prior. This formula I came up with myself. Why am I using this formula? I could have go to the bank where they make the coins, measure that press, and figure out the exact distribution of the biases. But I don't want to do that because I want to use a formula that works very nicely to this distribution here. It's a conjugate prior, meaning if I start multiplying them, I get the same kind of distribution. So let's do that. This will be probability of, I'm applying Bayes' theorem here, right? This is a different x, this is x prime. It's same like in there, summing up over all possibilities, right? So now I know this is my formula, right? S plus F, choose S, X, S plus alpha minus 1, 1 minus X at plus beta minus 1. So what happened here? How did I get this? I multiplied those two together, right? Because that's what it says here, multiply those two together. So how do I get S plus Fs? That's coming from here. Where is x at S plus alpha minus 1 coming from? There is an x at S in here, and there is an x at alpha minus 1 here. So how much is x at S times x at alpha minus 1? Is summing up the exponents, right? To follow this? Same thing in here. 1 minus x has the power f here. It has the power beta minus 1 here. So that's where I get the exponent f plus beta minus 1. And then I get beta divided by beta alpha plus beta. Where is this coming from? This stuff here, right? Okay. And this is the integral over all terms. Now, because it's a conjugate price, it's going to work out nice. It's going to be x at S plus alpha minus 1, 1 minus x at f plus beta minus 1, divided by beta function of S plus alpha, f plus beta. Let's see if anybody figures out why that is. So first of all, this integral here, it has nothing to do with alpha beta, nothing to do with S and F. So those two terms cancels out. Same thing with this, they cancel out. So then, where is S plus alpha minus 1 coming from? It's what's left here. Where is 1 minus x f plus beta minus 1? It's what's left here. So how do I think everybody can see where the numerator is coming from. What happens to the rest of the integral? So once this term here cancels out with this, and these terms here cancels out with this, what's the integral on x prime from this? That is effectively a normalization constant from the numerator, right? But by definition, this function, the normalization constant is going to be this beta function. You can prove that beta function is the integral or the sum, the discrete sum over these values here. So it needs to be that because this has to be a probability, so it has to be normalized with the proper constant here. So this in here is just another beta, a new beta distribution. A beta distribution looks like this, right? Didn't we say that somewhere? Beta distribution looks like that. It's a parameter q at some power, 1 minus q at a different power. And it has to be normalized by the beta function to be a proper distribution. Isn't this having the same shape? Is x, some value x at some power, 1 minus x at a different power, and then normalize at the proper things, right? 1 plus this, 1 plus that. This is the two coefficients in beta function. Isn't it the same thing happened here? If I had 1 s plus alpha, that's s, right? F plus beta is this one. So this is simply a new beta distribution in coefficients. S alpha plus s and beta plus f. So this is how conjugate prior works. If my distribution over parameters had a beta, was a beta model, and I have a coin flips function that's saying this is the conditional one way, this is this here, given the parameter, how likely am I to observe certain successes and failures in so many trials. Then when I update my posterior over the parameters, now that I've seen so many successes and failures, I re-estimate my parameters, right? If I started with a fair coin, 50-50, right? There is a beta distribution that's pretty close to a fair coin. once I see a number of successes and failures, maybe I should update my belief in what the parameters were. Maybe my parameters initially were not quite right. Now that I observe data, I'll say, okay, change my belief in the distribution over parameters. It's a new beta distribution. So I can repeat this process. The more I flip the coin, the more I'll get a better sense of what my distribution is. This distribution will be very skewed eventually. Will pinpoint to the exact bias of the coin if I have enough evidence. This is how conjugate priors work. Yes?
Can a survey distribution have more than one conjugate prior?
There is a large table on Wikipedia with, for each distribution, what is the conjugate prior. So you can study that. Not all distributions are easy to get their conjugate priors, but in data problems, it's easy if whatever our model has to correspond to reality, like these coins. I'm using the binomial distribution here because the coins, I think, follow binomial distribution. If I want to do that, and this is a Bayesian process where the more evidence I see, the more I update my prior, right, or the parameters, and then I see more evidence and I update my prior again. To do that easily, it's better to start with a conjugate prior. The process is going to be nice and smooth that way. Okay? So now we've got the process of conjugate priors. We've got Gibbs sampling. We need to move towards LDA, right? So let's, that being said, let's see how I can apply Gibbs sampling for LDA. So the paper that I'm going to follow and that you should follow, it's one of the easiest I found. It has a few mistakes in it, I think. So I have to correct them, and the version online will have these corrections. Mostly typos. It's not the best paper, but I think it's the easiest one to follow, which for me is more important that you guys have the right intuition, even if the math is a little, left out in the details. So how do we do LDA? Back to LDA, remember? We have words in documents. These are all vectors of words in documents. You can, I think the notion here is that the word I is the ith word in the collection. You think of all these documents of a chunk of words, and there's n words. In all docs, which are D1, D2 up to D something. Think of them as putting all the documents one after the other, getting word after word after word in those documents. So what we want here is to get topics. The topics K is a distribution over words. So that distribution we're going to call phi k. And the document D is represented as a distribution. Let me write it here, pk over words. Distribution pd over topics. Anybody run LDA already? Okay. Not too hard to run the package from Python. We're going to try to figure out how that actually works. For each word, very long. So let me make stuff more clear a little bit. This is correct. Each topic is a distribution over the words, right? So what I'm going to have is some sort of, this is a discrete distribution. Discrete meaning how many possibilities are, if I say distribution of words, what's the size of this discrete? What's the support? Number of words, right? So this is over vocabulary. And this is also discrete. So for a document that's represented at this theta d, what are the distribution? What's the support? Number of topics, right? Of the topics. Let's say this is vocabulary. I think the vocabulary is W or something like this. And this is the number of topics, big A. But there is a prior over topics that is a function Dirichlet of some parameter beta, which is the probability of a particular topic. This is the prior probability. And there is a prior over documents. That's another Dirichlet probability prior over some document. So two things. What is Dirichlet? Distribution. This is nothing but a multinomial beta. So you saw how the beta worked out, where we had the beta function here, beta distribution. What did we have here? Was a bunch of, it was this Q parameter at some powers, and then normalized with the beta function to get it to 1. So if I don't have just one Q and one minus Q, suppose I want to have a multiple values that sum to 1, right? Q and 1 minus Q sums to 1. Suppose I don't want to break it into 2 parts, Q and 1 minus Q. Suppose I want to break it into 10 parts. How would that work? Would be what? Q1 at some power alpha 1 minus 1, right? I'm looking here, I'm trying to replicate this for more than 2 parts. Times Q2 at alpha 2 minus 1 times QT at alpha t minus 1. And the sum of QI's have to be 1, because those two Q sums there. And then there is a beta that has to be on all the alphas, right? Alpha 1, alpha 2, alpha t. Right? We already said that somewhere in here, that if you want to have a beta of multiple ones, there's a function that does that. So Dirichlet is like the beta distribution, but now with 2 things, but with many things. And why did I pick this Dirichlet? Why did I pick here this beta? It's the conjugate prior of this function. So why did I pick the Dirichlet here? Because these discrete distributions, they multinomial. I think if I generate documents and topics that way, I'm essentially playing with, like before with the coin flips, but the coin had only two possibilities, right? That's why it's binomial. Every time I draw a topic or a document, right, from a discrete distribution, I'm going to imagine myself flipping a coin, except the number of possibilities is not two, is many. If I pick a topic, how many possibilities do I have? Okay. If I pick a document, it's or a word or something, it's how many words I have. So I'm going to say those discrete distributions there are independent draws from a discrete distribution. Independent draws from a discrete distribution always going to cause a multinomial. Right? Every time you have an independent repeated draws from the same distribution, you get a multinomial function. The binomial function has the conjugate prior this beta function here. The multinomial, which is extended of binomial, is just binomial with more than two slots or support, will have the conjugate prior, the natural extension of the beta distribution into more than two support, which is the Dirichlet distribution. So the reason I'm picking those priors to be Dirichlet is not accidental. Is because the conjugate prior for multinomial is how do I know that? I have this table, right? If I look in the table at multinomial, what am I going to see? What's the conjugate prior for that? Dirichlet. Of course, there's a proof, like the proof we did here for that. There's a similar one. It's just, instead of two, there's like t terms that the proof is the same. So a lot of these, why do I make a big deal out of this? I'm such a big fan of LDA? No. A lot of these ideas apply in all Bayesian inference, whether it's coins or documents or patients or sampling images or stuff like that. You're going to see these ideas repeating. Some distribution is your understanding of modeling reality, multinomial. That has to do with, you think, independent draws from a fixed distribution that's going to be multinomial. Now, if the draws are not really independent, it may not fit the model so well. But we have an understanding of what the generative process does. Based on that, we need a prior that facilitates computation. And that prior is typically, in Bayesian inferences, the conjugate prior, that allows us to just update the prior as we see more evidence and keep it the same form. In this case, it would be a beta or Dirichlet function. And so, with this idea, we're going to have here the topic modeling. We've written this differently before. This is a vector of words, topics, documents. This is the priors over documents, priors over topics. So, given some parameters, this is a very generic form. Which ones are the priors here? First two are priors, right? And what is this? Probability of topics given the documents, and this is probability over of topics given documents, and this is probability of word given topic. This is prior over topics. It's prior of documents. So now, I'm going to write that a little bit different. And alpha, beta are what? Vectors of parameters, right? Because in Dirichlet distributions, alpha is actually many alphas, right? So alpha, betas are parameters. Vectors. It's a little bit like Bayes' theorem, but with conditionals, with more conditionals. This is a typical exercise for Bayesian inference, how to write Bayesian theorem with more than two variables in it. So if you think of alpha, beta as just parameters and ignore them for the moment, this is the joint without alpha, beta, the joint in the other variables, divided by P of W would be the probability of the other three conditional in W. And you can show quite easily with Bayesian theorem that this holds if everything is conditional also in alpha beta. It's not too different than the typical Bayes theorem. Right? But what's the intuition here? In English, this is the probability of the distribution over documents, the distribution over topics, and the actual topic assignment. D is the topic. We're going to talk about that in a second. Per word. So this is the particular distribution over documents, topics, and assignments of words to topics, given words that I observe, because that's what I'm given in LDA, words, right? And the parameters that I have. Right. So in here, this is just Bayes. This is how to compute this. This is where I'm going to need Gibbs sampling. Right? But there is one more trick in Gibbs sampling that before I instead of sampling conditionally like Gibbs did for every variable of the model given the previous ones that I sampled, the last versions of them, I could say sample only the topic Zi for word Wi given proper sampling distribution. So instead of doing the whole Gibbs sampling, I'm going to say the only thing I need to sample in this particular model is the topic for a word. The reason for that is that everything depends on that. It's called a sufficient statistic. Once I know the distribution for a particular word over topics, I can compute everything else based on that. If you pay attention to EM, there is that membership term, remember? the probability that that object goes to that cluster or something like this. Once you have that membership value, I think it's called gamma, everything depends on that value. Both the E and M step can be written by that function membership value, right? So both E and M step come down to, if you compute a membership, if you know what's the probability of every patient going to every cluster, then both E and M steps can be written in terms of that gamma. That's how EM actually works. Right? Same thing in here. This particular for this model, I only need to sample the topic given a word, because if I have that probability, I can compute everything based on it. So this is called a sufficient statistic. And this particular version of Gibbs sampling is called collapsed. Collapsed meaning the only thing you need is to sample the topic, because everything depends on that. I think we had enough, enough so much math that, you know, I want to show you the rest on a paper here. So there's a little bit more involved math here, but you won't need it if you want to implement LDA with Gibbs sampling. You only need, like before, the result update rules, which are quite easy. You'll see, once you settle on this thing, it's going to feel a lot easier than it felt 2 weeks ago. There is a paper that, again, I found the easiest way to follow, both in explaining the theory and the actual result in terms of implementation. The math is not complete, and I think they have some mistakes in there, okay? But I think it's the easiest way to translate this into an actual algorithm and the easiest way to follow the intuition of LDA. So in that sense, credit to this guy who wrote it that way, simpler than LDA original papers, but criticism to him that he didn't get his math right, okay? So what do we have in here? This is what we already said. If we think of the topics, distribution for a document into topics as discrete, and will be multinomial because we assume independence over the draws, same thing of the words in a topic, then we know that if those are multinomial, the conjugate priors we're going to use are the Dirichlet things. We get that from the table. This is the main equation of what we need to optimize. This is an example for a data set that if you want 3 topics, the labeling is manual at the top. But you can see that, like you guys are going to see in 20 news groups and in this DUC document data set, you should see words, high probability words in a topic, they kind of make sense. We definitely want those topics to be different than the neural network's hidden layer where nothing makes sense, right? In here, it's pretty easy if you look at these high distribution words in this topic to tell, okay, I think I know what this is about, right? This is about environmental problems. This is the famous Enron scandal where they spilled oil and there was some problem with that, right? Very famous bunch of emails related to that scandal. Here's traveling, and here's fantasy football, right? So this is clearly, you want the topics to be independent and to make semantical sense. So how do we get here? This is what we said we want, this equation we just put on the board. This is a little bit of Gibbs sampling that we already know. and the collapse Gibbs sampling. So this is what we're going to do in the collapse Gibbs sampling. Instead of estimating every variable that we need, which we could do in principle, we're only going to say what? We want to sample the topic from word I, given all the remember minus I, what it means? All the ones except I, right? Parameters in the words observed. So this is a little bit of Bayes' theorem. That's easy because you just follow Bayes. So Zi, Zi minus 1, alpha, beta are here. You can ignore alpha, beta for the purpose of Bayes, and we get what? What did we move from? Instead of Zi given Zi minus 1, we get the joint here, and in here we get Zi minus 1 is the the normalization. Is that right? So P of Zi minus 1 and W, if I multiply with this conditional, I get the joint, right? Because this is Zi, Zi minus 1 and W, so I get the joint. And now I further say this thing here, it's proportional with this. Proportional as in I'm skipping the normalization term. It's the same like when you take our maximum likelihood. You don't need to normalize because if you take our max, you can have the probability it's unnormalized. Maximum doesn't changes by normalization, right? And this is saying that probability of a Zi and Zi minus 1, it's actually the probability of the whole Z. Now, where is this question?
Yeah, in the formula, if you say it represents Bayes' theorem, where's the probability of what we usually multiply the prior probability, right, in the numerator?
This is not exactly Bayes' theorem. This is saying a joint is like P of x and y is P of x times P of y given x. So this is a joint. This is P of Zi minus 1 and W, the first chunk. And this is probability of the other variable depending on those two. And everything is conditional in alphas and betas as parameters.
So here we only sample like C's, right?
Right. We want to sample Zi.
Beta.
What?
How about FR and beta? FR and
F what?
FR.
Alpha, betas are parameters.
So we assume that we already got those.
Right. So let's not worry about that for a moment. Let's say we just fix them in advance. Although that's not true. The math that comes next has to do the conjugate prior, how the conjugate prior works. So I take that formula that I wrote, I do independence between the two parts that are independent, so I can split the multiplications into this one versus that one because they're independent. And now each one of them is a multinomial and a conjugate prior, right? This is the prior of the multinomial. Prior, and this is the multinomial. This is the prior multinomial. We already know we're gonna get the same form as the prior, just Dirichlet updated, because that's why we pick the Dirichlet, so that when we multiply with the multinomial, we get a new Dirichlet. Right? So that's what they show here. That if you do this, some math I'm gonna skip, there's a mistake here. There's a product missing that I'm going to add with my hand on the PDF, right? But apart from that, the reason this works that way, it's very similar to the proof I did on the board, because these exponents start combining themselves, you know, like the ones from the prior with the ones from the multinomial. And when they get sum of the exponents, this is another Dirichlet distribution here. Same thing happened for the other term. And then I have to compute the sampling probability, the collapse sampling, right? This is saying if you really want to compute Zi given the previous and all that, there is this monster. we trust that they got it right because they copied from the other papers. Okay, the other papers are very well known. The references are, those people are super famous. So there's papers with thousands of citations. We assume they got it right, because there's so many. But you can verify the math instead. And I get here. This is saying that I need to sample proportional with these quantities, right? This sign is proportional, right? Meaning without normalization. So assuming we trust this math, it's not really our job as computer scientists to, I think we need to understand where the math is coming from. And if somebody really asks you, your boss, hey, you need to explain this to me properly, you should be able to do that with significant effort. But it's not our job as computer scientists to develop this mathematics. It's the mathematician's job to figure out how beta distributions and all of that work. So I wouldn't feel too bad if I would say, like, how did they came up with this? Well, probably call a math friend and say, figure it out, right? But if somebody shows it to us, we should be smart enough to be able to parse it and understand. And this is nice. So this is not too hard to follow if you remember that gamma is like a factorial, right? This works with every value and things like that. So I get this. So now how can I use this to really implement LDA? That's it. That's the whole LDA that you have to write. So I repeat a bunch of loops because I need to keep updating, right? It's like the more evidence I see, the more I update my parameters. So that's the iteration. This goes from all the words across all documents. Imagine the documents D1, D2, D3, and then I have words 1 to N, where N is not the vocabulary size. N is the number of the words, total length of with repetitions, right? So word 1 is the first word in the first document up to word 257, which is the last word in document 1. Then word 258 is what? The first word in second document. That goes to say word number 395, which is the last word in the second document. So who's word 396? First word in the third document, right? So for every word WI, there is immediately the document it's coming from. So when they use D, who's this D here? That's the D for that word I, right? Because every word I is automatically part of a document. It's not specified, you have to dig it up, but that's what it is. This D is, for every word I know which document belongs to, right? Because those words are not the vocabulary, they are actually positioned in documents. So what this does, this is computing the sampling distribution, and where did they get this formula? It's the one just computed, right? NDK plus alpha K, NKW, blah, 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 blah. I think this is this formula right here. Right? So they compute the sampling distribution here. They have the thing with decrease by 1 because I don't want to use the current word for sampling the current distribution. Kind of thing. So you'd have to think a little bit, why am I decreasing by 1 before computing this, right? But then once I have the sampling, this is a discrete sampling distribution, right? So I have to sample a topic based on that distribution. So I'm sampling here. I need a mechanism to sample with ununiform probabilities, right? But I only need to sample one at a time. The complication with ununiform probabilities if I need to sample 3 or 4 or 5 objects at a time. But if it's just one, I pick a random number, I get the cumulative distributions, and I get the topic. So I get a topic. I update those plus, whatever I got. This is the how many times this topic has been selected for that document. This is how many times this topic has been sampled for that word. And this is how many times a particular topic has been sampled. And that's it. If I repeat this enough time, I got LDA. Simple, right?
So when do you stop something?
I'm not sure. I think this has to be some convergence criteria. Right, so I think when these numbers, when you start normalizing this, you get probabilities, because once you have these counts, you get probability of words for each topic, and you get probability of topic for each document. Once this probability starts stabilizing, like they're not changing anymore, it probably means that you kind of done. My intuition is that the more you go, the better, as in the more clear the probability becomes, the more saturated. But so it doesn't hurt to go more than what's necessary. But at some point you say, I don't benefit anymore for doing this. Right? So this is an extra credit exercise, because I think the behind the scenes procedure, not this is I think quite easy to implement, but behind it, to understand where all these calculations come from, it's I think beyond the scope of the class and details. But I do think it's worth the exercise to see, okay, first implement it and notice that it works or doesn't work. There may be some engineering tricks that you need to apply there to make it work. And then, given how much time you have, you can go over the math. The reason I did this, again, is that these ideas are not just for LDA. In a lot of Bayesian inference, you're gonna see a lot of these concepts: conjugate prior, Dirichlet, multinomials, so on and so forth. You should also know, as an alternative to Gibbs sampling, there is something called variational inference. So don't be surprised when a lot of these problems are written with variational inference as a method for doing them, not with Gibbs sampling. For some things, but I won't talk about variational inference, but for some problems, variational inference is easier or better. For LDA, and when I can get handle like that on conditionals, Gibbs sampling is preferable. The original LDA paper is written with variational inference, but then people have figured out Gibbs sampling is a better method to do that. Okay. So that's completely finishing the whole sampling part. And next day, Wednesday, we're moving on. You guys gonna have one more homework. That will be on drafts.